Hey everybody, welcome back to Young Engineers of Today. Uh, Amazing Mechatronics. Hey Ved. Um, so we're going to continue with the physical computing side of Raspberry Pi. I'm going to show you guys how to do it in Fritzing, certainly, well, connect circuits up and everything like that. And then I'll go back to the slides for the programming side of it because unfortunately, Scratch Online can't really uh, doesn't have the same options. Oh, that's okay. That's okay. I can at least show you how to do it in Fritzing, and then you can, when you have your own time, you can program it on the Raspberry Pi. It's not a huge deal if you don't have a breadboard. But the online Scratch option does not have the same programming blocks that the Raspberry Pi does. Specifically, the ones referring to GPIO pins and things like that. So let's spend some time reviewing what we went over last Thursday. So I showed you guys, I talked to you guys about what breadboards are. They have the ability to, you can rapidly prototype circuits by using breadboards because they can provide the underpinnings of a circuit. You can connect things together and change the configuration of a circuit very, very quickly, and it's very useful in that sense. It's not very good for a permanent circuit, but for a temporary circuit, certainly breadboards are very, very good. It basically just works by plugging in a component. And if you guys will remember, all breadboards have sort of these connected rails where they conduct electricity along them. So you can connect multiple components together even though you're plugging them into different slots. So despite that fact, you can still have a resistor connected to an LED because they're plugged in on the same rail. Now, remember that the rails run horizontally in the middle of the board, save for this middle divider, which splits the two sets of rails, splits the rows of rails into two sets. And then vertically on the sides, and they run from top to bottom on the sides because you can use those as power and ground rails, providing, not surprisingly, power or ground to your entire circuit, because sometimes multiple parts of your circuits will need power or multiple parts of your circuits will need a grounding or both. So they do provide that ability so that you can very easily create a common power line and a common ground line for your circuit. Because of this, though, you want to make sure that you're plugging in components across multiple rails, two rails specifically for most components, because otherwise you'll run into an issue where electricity will not actually travel down the component, because remember, electricity is lazy. It will always travel the path of least resistance. And a rail that conducts electricity is always going to have less resistance than any component, including LEDs and things like that, and very obviously resistors. We talked about LEDs. LEDs have a polarity, that is to say a right and a wrong way to plug them in. You want to make sure you don't plug them in backwards, because since LEDs are a form of diode, we can think of diodes as one-way streets for electricity. They'll travel one way, but they will not travel the other way. So if we plug it in backwards, we essentially break the circuit. So just remember, the longer leg goes towards the power and the shorter leg goes towards the ground. The longer leg is referred to as the anode, and the shorter leg is referred to as the cathode. If you're ever not sure, because sometimes when you're soldering a circuit together, you might clip some of the excess metal off the legs or something like that in order to bring it closer to the breadboard. LEDs are also going to have a chunk taken out of the this little lip here at the bottom of the plastic, and wherever that chunk taken out is, it's going to be where the cathode is, which is the minus leg, the smaller leg, which is the one that goes towards the ground. So, I mean, I'm saying that now, that's just something that you'll want to keep in mind in the future when you're building circuits and things like that. If you don't remember it perfectly right now, that's okay. As you get more comfortable with components, you'll certainly get more comfortable with correctly plugging in an LED, determining which way is the correct way and plugging it in that way. Then we've got resistors. Resistors reduce current by turning electrical energy into heat energy, essentially. And remember, resistors are very, 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 very small, so you can't really write numbers that denote the amount of resistance that a resistor has. which is measured in ohms, which is the little omega symbol, the capital omega. So the way we tell that is by reading the colored bands on a resistor. Remember, we get a two-digit number using the first two bands, certainly in the case of a 4-band resistor. So in this case, 3 and 3, which gives us 33. And then we get a third band, which tells us what power of 10 to multiply that by. And this is 10 to the 1, so we multiply it by 10, which gives us 330. And then remember, the gold is for the tolerance, because we have a listed value for a resistor and an amount that a resistor can actually resist based on, impurities in the material and, in the manufacturing process and things like that. So sometimes they'll resist a little bit more than their listed value or a little bit less than their listed value. And we always want to just check the band to see how wide that spread can be. And it's usually in a percentage value. So given all of that, this is the circuit we're going to end up building, essentially. The battery is going to be replaced with the Raspberry Pi, but it's just a very simple circuit, and then we're going to use the programming on the Raspberry Pi in order to control how the light blinks. Whether, well, we're going to control the light so that it blinks as opposed to just turning on and staying on. That is going to be the ideal outcome in all of this. So it'll give us an introduction to hooking up electronics, as well as give us an introduction to programming on the Raspberry Pi for those GPIO pins, and it'll give us a little bit more experience with Scratch. So all of these things are good things. All of these things are useful, helpful things, and hopefully all these things are actually kind of fun too. So let's go ahead and this puts us right about where we ended on Thursday, so let's continue. So as I mentioned before, the Raspberry Pi has GPIO, or General Purpose Input-Output pins. I don't know why the P is capitalized there. It should not be. There we go. It's just a set of pins on one side of the Raspberry Pi, and basically they're pins that can be set up to be either input or output, hence the name General Purpose Input-Output pins. So you can run the Raspberry Pi and have a particular pin be outputs, then you can change the coding on the Raspberry Pi, make it an input pin, reconfigure your circuit, upload the code and run it again, and then that code or that pin will be taking in electrical signals. Now, it's not really possible to change a pin from input to output or vice versa in the same program. Once you commit to a pin being input or commit to a pin being output on a particular program, it will stay that way. However, you can have them be different between different programs. So you can upload a new program to the Raspberry Pi and switch a pin from input to output or the other way around. So that's certainly doable, and that's the power in the GPIO pins, is their versatility. Now, not all of these are going to be GPIO pins. Some of them are reserved for very specific things, and actually we'll take a look at what each of these pins does in the next couple slides here, and we'll use that knowledge in order to build a circuit off of it. But for the most part, the pins are customizable in that sense. Beyond that too, I don't remember off the top of my head, but we'll get to those slides and we'll be able to go over that. So we'll see, certainly. But off the top of my head, I don't remember if it's got a dedicated section to its own. I don't think it does, but I think there's a sensing or something like that will give us the ability to utilize the GPIO pins. So this is a diagram of what all the pins do. This is a pretty complicated looking diagram, so that's kind of annoying, but it wouldn't necessarily be a bad idea to just sort of have a diagram on hand for what the pins do, just because there's 40 of them. So writing it down would be annoying. Memorizing it, you can certainly memorize some of the pins, but by and large, this doesn't really follow a nice, easy it doesn't really follow a nice, easy pattern. It's safe to assume that there's about 3 GPIO pins before it gets broken up by another more specialized pin, but that's not exactly that's not exactly a perfect analogy. or a perfect description. So you might be better off just having, yeah, exactly, one more diagram from my information sheet. Precisely. You might just be better off having this diagram handy for whenever you're building a circuit with the Pi. So as you can see here, they reference a top of the Pi and a bottom of the Pi for basically orientation purposes. And the bottom of the Pi is where the USB and the barrel plug and all that stuff is. The top of the Pi is where the SD card gets plugged in, which contains, which is the hard drive for the Pi. So if you want to think about it like that, yeah, the top of the Pi is going to be where the SD card plugs in. The bottom of the Pi is going to be, this is actually not a barrel plug, this is the network adapter. It's going to be where the network adapter and the USB plugs are. If you set it up so that you got the pins on the right-hand side and the HDMI port on the left-hand side, you've got it oriented properly. And then you can look at it, you can look at this diagram and have it make sense. Now, you might notice that the pins are numbered horizontally. So pin 1 is the upper left, pin 2 is the upper right, pin 3 is one row down on the left, pin 4 is one row down on the right, and so on. So they actually alternate from side to side for their numbering scheme, which is a little unusual. I mean, it's actually not from the perspective of convention, but it is a little unusual to get used to if you're, not generally. Will alligator clips be useful here? Yeah, alligator clips could definitely be useful. They also have male to female jumper cables, and those would certainly work very well for something like this. In fact, I would probably recommend those just because alligator clips, the entire material that the alligator clip is made out of is conductive. So you could theoretically accidentally have an alligator clip, clipped into here, and it's also touching pin 3 in addition to pin 1. And suddenly you're getting additional sort of garbage signal, or you're short-circuiting your circuit by having power travel up to 3.3 volt in pin 1 through the alligator clip back down into GPIO 2 in pin 3. So alligator clips will certainly do the trick. They will work, although they'll have to be very small alligator clips, and you'll have to be very careful about how you plug them in. So for that reason, I would recommend male to female jumper cables, because the male end can plug into the breadboard, whereas the female end can plug into the GPIO pins on the Pi. Now, the problem with that is the fact that if you're plugging stuff in from breadboard to breadboard, you're going to need male to male. So you would need 2 sets of jumper cables or jumper wires in order to build a circuit in a Raspberry Pi, which is kind of annoying. I'm a little disappointed that they ended up going with male pins just for simplicity's sake. But, I'm not a designer for Raspberry Pi, and considering the fact that the Raspberry Pi is just a bare board, it's also not entirely, unusual for that kind of thing to be the case. Hence why male to female jumper wires exist. A PC the size of an Intel chip. Not quite. It's bigger than that. This would be a super big Intel chip. But yeah, that would be I think there are things like that exist. They're very, very, very small. Well, sort of, maybe, potentially, probably not though. Just because you need to have the CPU, you need to have a timing chip, you need to have RAM, you need to have a place to plug in peripherals and things like that unless you want it to be a completely headless computer. So for that reason, a Raspberry Pi does a pretty admirable job of fitting everything that it needs in order to be a fully functioning PC onto a single card or, a circuit board. Anyway, as you can see, anything labeled GPIO is going to be any of these GPIO pins. So they're going to be configurable to be input and output. You've also got these black ones labeled GND. That's short for ground. That will provide grounding for any circuits that you hook up to the Raspberry Pi. So it's important to note that there is grounding built into the Raspberry Pi. If you want to build a circuit and plug it into the Pi, you can use these grounding pins to plug into that common ground on your breadboard. Then you've got the yellow and the red, which are two different levels of power. You can provide either 3.3 volts of power or 5 volts of power, and that can be useful for whatever particular circuit you're running. You can run lower power in order to protect more delicate components, or you can run higher power in order to provide more power to components that need them. It's generally not recommended to, well, actually, you wouldn't be able to run both on a single circuit, but theoretically, you could have two separate circuits that are each being powered by, one's powered by 3.3 and one's powered by 5 volts. Now keep in mind that this is not a guaranteed thing. There are certainly issues with the Arduino where if you're hooked up to the 5 volt power, then the Arduino is sending out 5 volts through all of its pins, confusingly, because the little built-in voltage regulator, basically the thing that determines how much power gets sent out, senses that something's plugged into the 5 volt power, and so sends 5 volts out through all of its power pins. So that's something you want to be mindful of when you're building circuits for the Raspberry Pi. You might want to assume that you're going to be receiving 5 volts of power all the time if you have anything hooked up to 5 volts of power, which is just good practice anyway. But it's just something to keep in mind. So we've got GPIO pins, we've got grounding pins, and we've got power pins. That's enough to build pretty much most any circuits that we're interested in. You'll notice that 27 and 28 reserved pins, those are for specialized purposes. We're not even going to worry about that. Then you've got the two green ones, 8 and 10. They're listed as UART0 TX and UART0 RX. Those are transmitting and receiving pins. TX stands for transmitting, RX stands for receiving, or prescription, depending upon what industry you're in. But those are for communicating with another computer, essentially, something that will be able to read that information, because it can actually send out data as opposed to electricity, so a flat amount of electricity at a given time. It can actually transmit ones and zeros through those to something that would be able to read those ones and zeros and turn it into information that's useful for you or whatever component needs that information. So there's that as well. And then we got alternate functions. We don't really need to worry about those. Those are just additional things those pins can do. Additional interface protocols and things like that. Could the GPIO pins get damaged? Excellent question. Yes, they could. In a couple of different ways. You can either send too much power through a GPIO pin. Generally, that happens if you built a circuit that's sending too much power out. Maybe it's hooked up to a battery as its power source, and it's like a 9-volt battery or something like that. You could theoretically damage them by dropping them as well, but these things are pretty resilient. So it would take a fair amount of force in order to be able to bend or break one of these pins. I'm not saying test it. You definitely shouldn't do that, and you should treat this thing like it is reasonably delicate, because that's just a good practice to do anyway. But it should be decently resilient to physical damage, because the size of the pins versus their thickness means that and the metal that they're made out of means they're pretty resilient pieces of equipment. Oh, really? It happened to you, actually. Okay, so there you go. That hasn't happened to me before, and I've dropped this once or twice. But yes, then we have an example of that actually happening, dropping the Pi and having some of the pins bent. So yeah, then I would definitely say be very careful with your Pi. If it happens, it's okay. If the pins aren't broken, like if there isn't actually a physical break on the pins, they should still, transmit electricity and receive electricity and be hooked up to the Pi, theoretically, barring very special, unique cases that just would be bad soldering jobs anyway. Even if they do break, the part that's still connected to the Pi will still be connected electrically to the rest of the Pi. Now, the other one I was referring to is sending too much power through. That's a more insidious one, because that one's more difficult to pinpoint. If you end up sending too much power through, you can end up frying basically not just a pin, but the circuit that pin is connected to on the Pi. very, very worst case scenario, you could end up frying the CPU on the Pi. So generally, just to be sure that you are only sending power through that the Pi can manage, any circuits you build should really only be powered by the Pi, because 3.3 volts and 5 volts are meant to be within spec for the Raspberry Pi. If they can send that kind of power out, they will be able to receive that kind of power as well. So that's why you'd want to be sure that you do that. Yeah, let's be sure to start at the top of the Pi before trying to identify a Raspberry Pi GPIO. Yeah, right, we already knew that. We already knew that too. Oh, okay, so the Broadcom labels will be used as well, the ones that are labeled BCM, but we won't worry about that today. We'll cross that bridge when we get there. Wait. Oh, okay. Never mind. Never mind. Yeah, and confusingly, there are there are numbers for the GPIO pins as well as numbers for the pins themselves. So GPIO 2 is the same as pin 3. GPIO pin 18 is the same as pin 18. And in fact, I believe that's the only one that actually nope, that's not actually, that doesn't line up. That doesn't line up at all. Pin 18 is GPIO 24. I don't know why that says that. Okay, well anyway, I'll be referring to the names of the pins when we program them. So I'll be saying GPIO 2. I'm not going to say, you know, pin 3, even though that's what I mean, generally. So the first thing we're going to do is we're going to use our Raspberry Pi to light up an LED. Very, very easy. We're actually going to do this without any programming at first, and then we will go ahead and set up scratch programming. So this is just so you get a good feeling for how everything's hooked up on a breadboard and onto the Raspberry Pi. So let me go ahead and start up Fritzing so I can show that to you guys. Whoops. So I don't know if any of you happened to open Fritzing before the class today. If you didn't, that's fine. I never actually explicitly asked you to, so there was no particular reason why you guys should actually be compelled to do that. I just thought maybe you might have gotten curious and opened it up, but this is what it looks like. There's a lot going on here, but it's actually not quite as bad as you might think. And we'll spend some time getting familiar with the interface, some parts of the interface certainly, so that we know what exactly we're looking at and what to do with all this stuff. But anyway, the first time you open it, you're going to be looking at this, which is the welcome screen. It's going to give you news about Fritzing. It'll give you notifications for any new releases for Fritzing or anything that they've got coming up on the horizon, electronics-wise or anything like that. But this is something that you don't really necessarily need to pay attention to unless you start getting further into this and you want to do prototyping and things like that, and you actually become much more involved with Fritzing. As it stands right now, though, I'm just going to go ahead and skip all this stuff, and I'm going to look at these tabs that I have up here. I've got breadboard, schematic, PCB, and code. These are the different views for Fritzing. By default, you'll open up a new project just in the background the first time you open up Fritzing. So what I'm going to do is I'm going to go ahead and click on breadboard in order to bring us the breadboard view, and we're looking at a breadboard. Wonderful. Just as advertised. I can use the mouse wheel to zoom in and out. I can click the mouse wheel in order to pan the view around. I can also hold either left or right click in order to box select things, which is useful if you want to select multiple items. I can rotate a part by clicking on it so it's selected. See how I've got this dotted line around it? And then going up here to part and clicking on rotate. So I'm going to rotate it 90 degrees clockwise, so now it's vertical. Perfect. So now I have a vertical breadboard, which is going to be very useful. I can click off the breadboard in order to deselect it. Notice it does not have the dotted line around it anymore. Dotted line, no dotted line, dotted line, no dotted line. You get the idea. And then I've got a bunch of other stuff here. Add a note. I can also rotate down here. I can flip it down here if I was so inclined, flip it horizontally or flip it vertically, basically mirror it. I don't really need to utilize any of that stuff right now. Notes are just notes for yourself. Fritzing is a breadboard simulator. It's basically a circuit simulator. It's good for building circuit boards. So you can build a circuit on Fritzing. If you're satisfied with it, you can create a schematic out of it. Build your schematic and everything like that, and then you can organize a PCB and actually order that PCB to be printed out and delivered to you. So you could then have a circuit board of your circuit. If you had your own PCB maker, you could export this PCB code to your PCB maker, and you would have your own printed circuit board that you designed entirely on the computer that you could then use for whatever project you're on, which is pretty neat, I think. So anyway, we've got our breadboard here. As you can see, we've got a whole list of stuff over here. There's just a whole bunch of little pictures and everything. This is a list of all of the parts that we can connect to the breadboard and other things in order to build our circuit. So, at the top here, we've got resistors, capacitors, inductors, diodes, transistors, MOSFETs, things like that. Then, we've got buttons and switches and slides and thermometers and all kinds of stuff, and then we've got LEDs and speakers and displays and motors, and just there's a lot of stuff listed here. And we've got integrated circuits. That's what ICs stand for, so basically chips. We've got power supplies, microcontrollers, and in fact yes, the Raspberry Pi is listed among these components. We'll actually do a search in order to pull that up, but we can actually pull it down from computer over here as well. So anyway, I'm going to scroll back up to the top to basic, and I'm going to go ahead and I am going to grab one of these resistors and drag it out over here. That's all I did, was just click and drag, and now I have a resistor that exists. It's sort of out in this no man's land out here. It's you can think of, you just grabbed a resistor and placed it on your desktop so that you can plug it into the breadboard in a moment. And I'm actually going to grab an LED as well so that I have both of those. So now I have an LED and a resistor, and these are the components of our circuit, obviously, aside from the Raspberry Pi. Now I can scroll down here to computer, and I can see there's a little Raspberry Pi icon. If I mouse over it down here in the inspector, I can't actually move my cursor to show you because then it goes away if I do that. But underneath the parts list, there is that window labeled inspector, and you can see it says Raspberry Pi 3, and then it has a picture of generally the picture of the component as it appears on the breadboard view. Then it has a picture of it as it appears in the schematic view, and then I believe it also has a picture of how it appears in the PCB view, and then a little bit of description for it, and then properties. And some of these properties are actually modifiable. So we can worry about that in a moment because we will have to, but for now, let me just go ahead and drag this out. Now, if you aren't finding the Raspberry Pi, I can tell you that if you're looking in the parts window, you can see there's a whole bunch of stuff in this column on the left-hand side. It organizes by manufacturer, so we can pull up only Intel parts if we wanted to. We could pull up Seed parts if we wanted to. We could pull up SparkFun parts if we wanted to. All this stuff, and it's going to take a minute to load. Oh, what have I done? Yeah, there's a lot of SparkFun components. SparkFun is a very solid hobbyist brand. But at the top here, there's a magnifying glass, and it's the search command. And as you can see, I already typed in Raspberry, but you can do that. You could totally just type in Raspberry and spell it correctly, and there would be a whole listing of basically all the Raspberry Pis that that Fritzing offers. In fact, anything that has Raspberry in the name. So we're even getting Raspberry Pi Shields and GPIO Arduino, which is a version of the Arduino. It's basically a Pi with an ATmega 328, which is a microcontroller. So now we've got all of our components. I'm going to rotate my Raspberry Pi until the GPIO pins are facing the breadboard. And I'm going to rotate my LED so it's facing to the left. I believe that should be correct. If I mouse over the end of the LED, it'll tell me which ones are the anodes and which ones are the cathodes. So yeah, we'll go ahead and rotate it so it's facing to the left. Then I'm going to rotate my resistor so it's vertical. And this is so I can easily plug it into two separate components on Fritzing. Of course, it doesn't want it. There we go. Boom. Now, before we go any further, I want to actually change the resistance on the LED. I want to make sure that this, change the resistance on the resistor. I want to make sure that this resistor is actually providing more, good Lord, this zooms in a lot, providing more resistance than what we currently have set up for it. There we go. So what I'm going to do is I'm going to click on it, and as you can see, it pops up over here in the inspector. We can give it a more useful name if we wanted to. R1 is going to be good enough for now because this is the only resistor we're going to have on the circuit. And you can see under properties, we got family, pin spacing, package, power, resistance. Resistance, we can actually type in a manual value. So I'm going to go ahead and replace those 2s with 3s. So it's going to be 330 ohm. And on top of that, if we look at the resistor, the colors of the bands have actually changed. So now it's orange, orange, brown instead of red, red, brown because red represents 2. Red, red, brown would be a 220 ohm resistor. Orange represents 3, so orange, orange, brown would be a 330 ohm resistor. Let me go ahead and drag this onto the breadboard, just like so. And as you can see, these rails on the breadboard have lit up green or been highlighted green, and that means that there is a component connected to them. So now we don't have to eyeball it and make sure that our LED or our resistor is, our ground jumper is hooked up to the same rail as the resistor. We can actually just connect it to one of the ones highlighted green, and easy as that. Like I said, you just grab a resistor and you change it to be 330 ohms. It's not, there is no 330 ohm resistor listed here because it's listed as a 220 ohm, and then you change it to 330 ohm. But yeah, that would be where you would find it, is in the list of core parts under basic. It's just, it should be the very first part listed will be 220 ohm resistor. It's kind of confusing that they call it 220 ohm resistor. They might just want to call it resistor and then give it a default value of 220 ohms, because then that suggests that there are resistors of different resistances listed in the core parts. But this is not the case. It's just this is the only resistor that there is, and then you change it in the properties afterwards to be 330 ohms. So now we've got our resistor plugged in. Let's plug in our LED. So if I mouse over the ends of the LED, I can see one is labeled, or it's not going to do that. And let's try it again. One is labeled cathode, and one is labeled anode. Now, which one is the one that gets plugged into, gets plugged in facing the power? Does anybody remember? Yeah, exactly. That is, the anode is the one that gets plugged in facing the power. So let's go ahead and let's just drag it as is to right here. So as you can see, the cathode is plugged in to the resistor, because as we have it, as we're going to set it up, the resistor is actually between the LED and the ground. That's another nice thing about the resistors in your circuits, is generally it doesn't really tend to matter whether or not they're in front of or behind the component that they're looking to reduce the current for. Now, as always, there are exceptions to that, but for the sake of clarity right now, I'm just going to say that it doesn't matter. So now we've got another set of green slots, and these correspond to the anode on the LED. Again, if I mouse over it, I can see anode. So now I'll go ahead and pull up my, oh, this is a 340 ohm resistor. What? Is it actually, though? Oh, would you look at that? It is. Okay. So we'll keep it 330 ohm. It doesn't really matter. There's going to be a basically token difference between 330 and 340 ohms for something like an LED. It really doesn't matter. You might have something that's more sensitive in the future, in which case you certainly want to be certain that you're plugging in everything with the proper resistance and everything like that. But as it stands right now, since we're hooking up an LED, it really doesn't matter whether or not it's 330 or 340 ohms. It would certainly matter if it was 330 ohms or 1,000 ohms. That would make a big difference, even 500 ohms. But 10 ohms, not really going to matter. In fact, you should be able to just drag it onto there. Now, you might have noticed when I was screwing around with it before that the resistor wasn't exactly lining up with the holes on the breadboard. So all I did was I just dragged the breadboard down a little bit. I just sort of relocated the breadboard slightly so that when I dragged the resistor down, it was able to line up with the sockets on the breadboard. But you should be able to know that it's lining up because the breadboard turns, or excuse me, the resistor turns blue in the background. So as you can see right here, not blue, blue. This means it's plugged into something. So we'll go ahead and plug it in right there. But yeah, that's just how you connect it, is just by dragging it on. You might need to wiggle around the breadboard. That means, did you rotate it? Here, so like, it didn't even care. Odd. It shouldn't be turning red though. Is there anything that you've got on the breadboard or the resistor that isn't lining up? Or are you overlapping anything? Because you shouldn't be. It doesn't even care if you overlap. Okay, there you go. Well, there you go. Mystery solved. Anyway, so we've got the resistor and we've got the LED hooked up. Now what I'm going to do, this is the first part. This is just going to be providing constant power. We're going to do this without coding just so you guys can get an idea for what a circuit's going to look like. I know that's not exactly exciting, but it'll be good to just basically get an idea of how fritzing works in case you're working with it. Or if you're working on it at home, it'll be good to get an idea for how to connect a circuit together and get it up and running. And the nice thing about this too is it will be very easy to tell whether or not you have it hooked up properly. If you do not, the LED won't turn on. If you do, the LED will turn on. So it's just a very, very straightforward thing. So let me go ahead, and what I'm going to do is I'm going to reference my little sheet again. Yes, I do know that, but I want to show the sheet. Okay, so this is all so weird. Okay, so what I'm going to do is I am going to connect this slot right here to the common ground over here, and the easiest way to do that is just to mouse over a slot so it's blue and click and drag. Bam, and you draw a little line from one to the other. You've just drawn a jumper wire. Congratulations. And I'm going to draw one from the LED to the other horizontal, or excuse me, vertical rail. So I've got one running from, I've got the resistor running from the rail that it's on to ground, and then the LED running from the rail that it's on to power. They're also connected to one another, so this helps create a complete circuit. Now here's the other thing. We've hooked it up to power and ground, but we haven't actually hooked it up to the Raspberry Pi yet, so it doesn't really mean anything as far as we're concerned. You got to make sure that you do that as well. Strictly speaking, this isn't a necessary thing to do because we just have one power and one ground for this circuit. So really, it would actually save us a little bit of trouble to just plug it directly into the Raspberry Pi. I'm not doing that though because, well, I want to get you guys into the habit of setting up your power and ground rail whenever you're working with this stuff, because that gives you basically a better, more solid starting point for your circuits. It ensures that, you know, you can very easily diagnose what's hooked up to power and what's hooked up to ground. It reduces the number of connections that are made to the Raspberry Pi. It reduces the number of pins that you have to keep track of that are connected to the Raspberry Pi. It really makes your life a whole lot easier. So what we're going to do is we're going to hook up the common power and the ground, and then we're going to hook those up to the Raspberry Pi. So why don't I go ahead and do that? The common power we want to get 3.3 volts from, so I'll do the drag thing like I did before, and I'm actually going to hook it up to the 3.3 volt pin on the Raspberry Pi, which is this top one up here. If I mouse over it, I see Raspberry Pi 3v3. If I mouse over this one, see 5 volt power. Then I've got more 5 volt power. Then I've got ground, and I've got GPIO 14, so on and so forth. So I can mouse over this stuff and see what the pins are in Fritzing, which is a pretty nice thing. Now we've hooked up all these wires, but they're all blue, so not the worst thing in the world, but sometimes that can get a little difficult to keep track of which is which because they're all the same color. So what I'm going to do is I'm going to click on this wire running from 3.3 volts to the common power, and I'm just going to, over here in the properties, I'm going to click this little drop-down menu and set it to be red. I'm going to do that with this one as well. Whoops. Why red, you might be asking? Well, it's convention in electronics to color wires that have electricity running through them, like the power wires, to be red. Conversely, ground wires are labeled black. Black means dead, red means live, essentially. So now we've got the common power hooked up. We're going to hook up the common ground, and I'm going to double check and make sure, yep, that one is the ground connection on the Raspberry Pi, so I'm going to go ahead and drag one from there to the, to the common ground on the breadboard. Now this might look a little confusing because I have the common power running in between the two connections for the common ground, but essentially what's going on here is power is running down here, then up, then into that one. I mean, it's not flowing in that direction, it's actually flowing in this direction, but that connection has been made. Now, on the other hand, for the power, it's running down the red wire, down the common power, over the red wire, and then up into the LED, and so on and so forth, like so. So this is actually how we complete the circuit for our LED. If you're working on this at home, you can plug your Raspberry Pi into a barrel plug and see if your LED lights up. Unfortunately, Fritzing does not have the ability to simulate a running circuit, unlike things like 123D Circuit and stuff like that, or circuits.io. So that does make things a little bit more taken on faith. Taking my word for it at this point. But this is a complete circuit, and if we provided power to this Raspberry Pi, we would see the LED light up. Of course, assuming that the Raspberry Pi is on and everything like that, once it's fully booted up, it should start sending out power through the GPIO pins, or the power pins, I should say. So there you go. Now, I said we were going to make an LED blink, and that's not actually the first thing we did. So what am I talking about here? Well, let's go ahead and actually get that set up. So we're going to slightly modify our circuit so that we can make sure that the Raspberry Pi has control over whether or not the LED lights up. That's going to be our goal. We're going to do that on the physical side of things, and then I believe that's really all we're going to have time for. So on Thursday, we'll get started on the coding side of things, and we'll get that set up. All right, so there's that, boom, 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 boom. So we got two separate circuits hooked up now. And that is hooked up, I see, okay. No, they're both hooked up to 5-volt power. This is not what I'm interested in. There we go. Okay, so they didn't actually update the slides. So let me go ahead and I'll just do this manually here. So what we're going to do is we are going to hook this power up to a GPIO pin. So our power rail will actually only provide power whenever we're sending information out on a GPIO pin. This is a little bit counter to convention, but whatever. So I'm going to just hit, with it selected, I'm going to hit the delete key on the keyboard, and boom, it disappears. So now we have an incomplete circuit because we're not actually providing power, right? We have a ground, but we're not actually providing power to the circuit, so nothing happens. So let me mouse over these. So GPIO 17 is the one we're interested in because that's the one we're gonna mess around with in Scratch. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is going to be pin 11 on the Raspberry Pi, GPIO 17. So it's the 6th one down on the left-hand side. And I'm just going to drag one from here to here. Boop. Turn it into a red wire so I know that I'm sending power out on it. And that is going to be actually our circuit for the programming next time. Now, I know we've got some time, certainly, but we're not going to really have enough time in order to get started on the programming aspect of this. So I want to fully introduce that, give you guys some time to take some notes on it and everything like that. So I don't want to throw it in at the end and rush everything here. I just want to make sure that we get the physical side of this done. But this is the circuit we're going to use for Thursday. This is a complete circuit. Well, assuming that we're sending out power on GPIO 17, this is a complete circuit which will provide power to the LED, light it up, but not too much thanks to our resistor, and then it'll come back out through the grounds into the ground of the Raspberry Pi, and that will be everything we need to do. But yeah, on Thursday, we will actually get into the programming aspect of this, so I'm going to go through how all the programming's done, all the things you need to do. It's actually very simple, so we can probably spend maybe like the first half hour going over the programming aspect of things, and then we can jump straight into more complex projects after that. If that sounds a little bit intimidating, don't be. It's really not that bad. But I want to make sure that you guys understand basically how the hardware and the software interact with each other, what exactly the interplay is for something like a Raspberry Pi, or in the future an Arduino. But let me go ahead and we'll do the poll questions, then we can leave it open for question and answer time. Give you guys ample time to ask any questions that you might have about what we've gone over today, or what we might have in the competition. I see Mr. Dubik is here as well, so it's possible he might be able to help out with some questions. If not,
I think we can try to help out. Yep, Tom, we can.
All right, for sure. But so sorry, I'm not entirely sure I understand your question, Ved. So transmit power via GPIO 17, and then are you asking what would happen after that? Because that would be a complete circuit. Nothing would happen after that. The LED would turn on whenever it's transmitting power. Okay, gotcha. That's all. There was just a little bit of confusion there. All right, so let me go ahead and do the poll questions, and then we'll do question and answer time. And then after that,